IB Biology Ecology Part IV will focus on climate change. The essential idea is the concentration of gases in the atmosphere affects climates experienced at the Earth's surface. Here is the outline of movies available for this unit. Use this outline to choose the movie you need for review. This movie is focused here. Global temperatures and climate patterns are influenced by concentrations of greenhouse gases, and climate change is just an enhanced greenhouse effect. It's an increase in the Earth's average temperature that's correlated with an increase in greenhouse gases in the atmosphere. Human activities are increasing the greenhouse gases in the atmosphere, and those activities are burning fossil fuels, deforestation, rice and cattle farming, use of chlorofluorocarbons in refrigerators. Human activities are contributing to an increase in atmospheric carbon dioxide. Human activities are contributing to an increase in the atmospheric greenhouse gases. Those activities are burning fossil fuels, deforestation, rice and cattle farming, use of chlorofluorocarbons, CFCs, in refrigerators and air conditioners, use of nitrogen fertilizers resulting in nitrous oxide, and cement use, which also adds carbon dioxide to the atmosphere. So here's the first IB syllabus statement of this movie. Describe the anthropogenic contribution of carbon dioxide to the atmosphere. Anthropogenic means of people origin. Carbon dioxide resulting from the activities of people. The primary activity increasing greenhouse gases, primarily carbon dioxide, would be fossil fuel combustion. Deforestation, in other words, taking down the trees that would otherwise remove carbon dioxide from the atmosphere, would result in leaving more carbon dioxide in the atmosphere. Deforestation contributes to carbon dioxide in the atmosphere. Rice paddies and cattle farming increase the level of greenhouse gases in the atmosphere. The anaerobic digestion of organic matter in the watery environment of rice paddies or in the guts of cattle releases methane to the atmosphere, and methane is a greenhouse gas. CFCs are molecules released into the lower atmosphere due to human use of refrigerants and air conditioners, foam packaging, and so forth. While the quantity of CFCs being released into the atmosphere has been reduced significantly due to the Montreal Protocol of 1987, some CFCs continue to be released, and they are greenhouse gases that contribute to climate change. The use of fertilizers in agriculture results in nitrous oxide, N2O dinitrogen oxide, which is also a greenhouse gas. Methane is released from Arctic habitats when the permafrost melts, thus resulting in the release of methane to the atmosphere. Or methane is released when the glaciers retreat, exposing peat, resulting in methane released to the atmosphere. This pie chart displays the relative importance of carbon dioxide as a greenhouse gas. Carbon dioxide is the most abundant greenhouse gas, along with water. But remember that methane and CFCs and nitrous oxides absorb long-wave radiation more effectively than carbon dioxide. Both abundance and the relative ability to absorb long-wave radiation contribute to the effectiveness of the gas as a greenhouse gas. Both abundance and relative ability to absorb long-wave radiation contribute to the effectiveness of the gas as a greenhouse gas. While methane and nitrous oxide and CFCs are lower in concentration in the atmosphere, these gases absorb long-wave radiation better than carbon dioxide. Again, here is the list of human activities causing an increase in the concentration of greenhouse gases, resulting in the enhanced greenhouse effect known as climate change. Study this list. Here's the next IB syllabus statement, but it should be an easy target at this point. State that recent increases in atmospheric carbon dioxide are largely due to increases in the combustion of fossilized organic matter, coal, oil, or natural gas. No one disputes the relatively recent increase in the concentration of carbon dioxide in the atmosphere. The data displaying the trend of increasing atmospheric carbon dioxide levels, seen here, is well regarded, having been measured and corroborated by instruments in different locations. Remember that the slight fluctuations seen here are due to seasonal temperature changes in the Northern Hemisphere. During the winter in the Northern Hemisphere, photosynthesis slows, thus carbon dioxide levels are high, while in the summer, when warm temperatures stimulate photosynthesis, carbon dioxide levels are lower. Despite the increase over the last 150 years of various greenhouse gases, seen in these four graphs, there are climate skeptics that remain firm in their thinking that the increase in the Earth's average temperature is caused by natural climate cycles over long periods of time, rather than anthropogenic causes. So here is the important IB syllabus statement. Describe the correlation between global temperature and atmospheric carbon dioxide concentrations. State that there is a correlation between rising atmospheric concentrations of carbon dioxide since the start of the Industrial Revolution 200 years ago and average global temperatures. The Intergovernmental Panel on Climate Change put out this graph showing the correlation between past temperatures and carbon dioxide concentrations in the atmosphere. What's interesting is that it shows carbon dioxide increasing and temperature increasing, but that the temperature increases after the carbon dioxide increases, and that there's a time lag. You can see the lag in time here. Carbon dioxide increases first, and then temperatures follow. This would be the model of today. We're combusting fossil fuels, so the carbon dioxide increases first, and then temperatures follow. Now, while this graph goes back 160,000 years, what's interesting is that it conflicts with other data, ice core data, that shows the historic relationship between carbon dioxide and temperature to be different. In other words, showing a different cause and effect. Is it that CO2 causes temperature increases, or could it be reversed? The ice core data, the data that stretches back 700,000 years, suggests that the relationship is the reverse, that temperature increase causes CO2 to increase. So this becomes part of the controversy. What parameter forces the other? Does CO2 increase force a temperature increase, or does an increase in temperature force an increase in CO2? Now, I would like to add my own editorial comment here. I think both scenarios are possible. Either parameter, temperature, or carbon dioxide could force the other, so that to lock yourself into the assumptions embedded in one data set or the other would be limiting. A graph like this one can be used to convey various pieces of information. It's important for you, whenever you read a graph, to be a discerning reader. Look at the x-axis carefully. Notice that this graph does not go back very far in time. And we can see the carbon dioxide concentrations here on the y-axis and average surface temperature on this y-axis. The carbon dioxide concentrations are increasing, and this is not disputed. The data from monitoring stations in Hawaii and Australia are reliable and well regarded. The temperature fluctuates around the CO2. A proponent of anthropogenic climate change would say, look, the temperature is going up and it's following the increase in CO2. And this is what's being observed. As the CO2 is increasing, the temperature in turn is also increasing. The climate change skeptic would say, but this graph only goes back 40 or 50 years, so how do we really know that these temperatures are higher than they have been in the past? This is a graph that shows instrumental temperature change over the last 150 years or so, and the data has come from thermometers. On both counts, the data is reasonably more reliable. Climate change proponents would argue that what's important about the data is not so much the high temperatures at any one moment in time, but the rate of change as seen in the slope of the curve, that this much change over a relatively short period of time indicates climate change. So that brings us to this IB syllabus statement. Evaluate 3 lines of evidence that leads to claims by some people that human activities are not causing climate change. I've laid some groundwork for this statement in the earlier slides. The Earth has had variations in its temperature over time for a variety of reasons, and I would like to present those reasons here. There's variation in the Earth's position relative to the Sun. Some orbits are more elliptical than others, and you can imagine how that would shift the Earth's temperature over time. Secondly, the Earth's tilt is not always 23.5 degrees off the vertical axis as it is today. The angle of rotation rocks back and forth from 22.5 degrees to 24.5 degrees, and the tilt of the Earth affects the angle at which solar radiation strikes the Earth. This would affect regional temperatures across the globe. And lastly, the Earth wobbles in its rotation, a process called precession, and this influences the Earth's temperature. These three processes cause variation in the Earth's temperature, and they are cyclical over long spans of time. I'll show you more on this in the slides to come. Here's a graph that shows time here along the x-axis back to 1 million years ago, and there are the different cycles of the Earth's position relative to the Sun, and we have sunspots here and stages of glaciation here, but we can focus on the bottom to see that there are times when the Earth is warmer and there are times when the Earth is colder. And you may be asking, well, how do we know that? And that's a good question, but we'll leave it for later in the movie. But you can see the cyclical nature of the Earth's temperature over time, and that's the most important thing for you to take from this slide. You may ask why the Earth is hot during certain periods and cold during other times, but that has to do with the interaction of these four processes that influence the Earth's temperature at any one moment in time. Here are two graphs that show sunspot number, and you can see how sunspots increase and decrease over time, and you can imagine this would be partly responsible, for altering the Earth's temperature. So you should be asking yourself the question, are we recording warmer temperatures today because of a higher sunspot activity? So how do we estimate the temperatures of the Earth before 1850, before a time when we had thermometers that we would deem as reliable instruments? What we use is what's called proxy data, indirect data, so that all of our estimates of temperature prior to 1850 would be indirect proxy data. To estimate past temperatures, the following indirect measurements are used. First, tree ring analysis. We have trees that will live between 3,000 and 6,000 years, and we can examine the rings to see the years that have been strong in growth and years when growth has been poor, and we can interpret that data to indirectly estimate temperature and possible carbon dioxide levels. Secondly, we have human records of crop harvests, good years and bad years, and we can interpret that with respect to the Earth's temperature. And thirdly, we have ice cores that provide data stretching back 400,000 years plus, and we can measure levels of carbon dioxide in bubbles of air trapped in the ice, and from those levels of carbon dioxide, we interpret temperature. And lastly, we can look at tree line data along mountain slopes. When the tree line goes up slope or down slope, we can interpret these changes with respect to the Earth's temperature. Before leaving this slide, let me remind you that in using proxy data, indirect data, there is greater uncertainty. The plus-minus error is much larger, and I'll be showing you some of that in the slides to come. Here's a slide to show how we use tree ring analysis to indirectly estimate temperatures. You can see a wide ring right here indicating a good year of growth, warmer temperatures. And we have some rings right here that are narrow indicating poor growth, a cold year or a dry year. Again, we have trees that live from 3,000 to 6,000 years, and we can analyze the rings to interpret past temperatures. In this graph, we have Antarctic ice core data that goes back 400,000 years, and the red curve is carbon dioxide data, and the blue curve is temperature data. Notice that the blue curve, temperature, rises first with the carbon dioxide following. Temp first, CO2 follows. So ice core data suggests that temperature increase precedes carbon dioxide increase. But today, we see the situation reversed. Carbon dioxide increases first and temperature follows. This is part of the controversy. Keep your mind open, remain aware of the uncertainties in the discussion. It's possible that, historically, temperature increases did force CO2 increase. But in today's world, that's not the case. that with the combustion of fossil fuels, carbon dioxide increases are forcing increases in temperature. Here are images to show how ice cores are done. A drill bores deep into the ice on Antarctica or in Greenland, and these cores are drawn from the ice and saved, preserved, kept frozen. The bubbles of air trapped in the ice are analyzed for the concentration of carbon dioxide. These cores are deep enough to go back 400,000 to 700,000 years. So here at the top of the slide is the list of indirect data sources. Remember that indirect data have greater uncertainty. And what's done is that the indirect proxy data gets averaged. All the various data sources get put together into a single line, even though not all the units are the same. How do you average tree ring width with human records of crop harvests with carbon dioxide levels out of bubbles in the ice? How do you average that? These data are not similar numbers and they don't have similar units, but people will put them together to make an estimate of past temperatures. And then at the very end of the temperature curve, we attach the modern thermometer-generated temperature record. So various scientists have attempted to reconstruct Northern Hemisphere temperatures over the last 1,000 years or so, and each of these curves seen here represents a different reconstruction. And you can see how different the reconstructions are. But the question is, which one is most accurate? The most recent research is represented by the red line, and according to the red line, temperatures are rising as we approach the year 2000. Now, just a quick note, instrumental thermometer records are presented by the black line here, and you can see how it is simply attached at the end of the other curves, and you can see that the Earth's temperature again appears to be increasing. Now, as you look at a graph like this and you see this very high temperature here, appears to be quite alarming, keep in mind that the data presented only goes back 1,000 years, so how do we know that this value is high relative to temperatures in the deep past? Now, this is a very interesting graph put out by the Intergovernmental Panel for Climate Change in 2001, and the data in blue is the proxy data, tree data, coral ring data, ice cores, historical records, etc. The black line is the average of all that proxy data. This is what gets done. Smart statisticians average the various forms of indirect data to produce the black curve that you can see running here. This is a way to understand past temperatures. Now, out here to the right, we see in red, this is instrumental data, thermometer data, and it's attached at the end, but you can see how the temperature is rising. In gray is the standard deviation of the data. Two standard deviations, actually, to present the greater uncertainty in the proxy data. But what you should notice is that uncertainty is quite large. In fact, at any one time in the past, the temperature might have been here or here or here, nearly as high as directly measured temperatures of today. Thus, there is a lot of uncertainty in understanding the high temperature of today. So this brings us to the next IB syllabus statement. Outline the consequences of a global rise in temperature on Arctic ecosystems with reference to the release of methane from peat in the tundra. I've already done that. Refer to a positive feedback loop and provide a brief explanation for the presence of the methane stored in the soil of the tundra. Let's look at those consequences of a global rise in temperature on Arctic ecosystems first. There would be an increased rate of melting of the Arctic ice cap. This would be a loss of ice habitat, potentially a loss of the polar bear. In this slide, we can see the decline in the Arctic ice cap from 1979 to 2005. These images were taken at the end of summer in each case. It's important to note that the melting of the Arctic ice sheet does not raise ocean levels because the ice already sits in water. Polar bears live on the Arctic ice sheets. What's the effect of climate change if the Arctic ice were to completely melt in the summer? A thawing of the permafrost exposes peat and is likely to release methane. Methane is a greenhouse gas, and there's a positive feedback loop here. As the warming increases the methane, and the methane increases the warming. Scientists are working to measure methane release from the tundra. As the permafrost melts due to the climate change, methane is released, and the methane increases the warming that increases the melting of the permafrost that allows more methane to be released. This is a positive feedback loop where a change in a certain direction accelerates the change in the same direction. Global temperatures and climate patterns are influenced by concentrations of greenhouse gases. Coastal areas would be vulnerable to rising sea levels. Global temperatures and climate patterns are influenced by concentrations of greenhouse gases. There would be shifts in weather patterns, more energetic weather, more rainfall in certain locations, and more drought in other locations. A biome is a major regional biotic community, such as a rainforest, desert, or tundra, characterized chiefly by the dominant forms of plant life and the prevailing climate. Climate change will result in a northward shift in biomes, a northerly expansion of southerly biomes. And as you know, tundra regions would experience a thaw of permafrost in the summers, methane release would increase, and methane is a greenhouse gas, which increases the melting of the permafrost. Hopefully you see the positive feedback loop here. The thermal expansion of water would raise ocean levels. Coastal areas would be vulnerable to rising sea levels due to the thermal expansion of water. The melting of the Greenland ice cap or the Antarctic ice sheets would raise world ocean levels because the ice sits on land. As the ice melts, it would drain into the ocean. Let's be clear here, the melting of the Arctic ice sheet does not raise ocean levels because the ice already sits in water. For the Greenland ice cap and the Antarctic ice sheet, the ice is on land, its melting would drain into the ocean and raise world ocean levels. The Greenland ice sheet is massive. If the entire ice sheet melted and drained from the land to the ocean levels would rise 7 to 8 meters, nearly 25 feet. And the last IB syllabus statements of this movie, statements that should be familiar to you because I've covered them elsewhere, explain the cycling of carbon dioxide in and out of aquatic ecosystems and within aquatic ecosystems. Explain the threat to coral reefs from increasing concentrations of carbon dioxide in the atmosphere. As carbon dioxide levels in the atmosphere increase, the ocean absorbs more CO2 through diffusion. When oceans absorb carbon dioxide, they become more acidic. This is carbonic acid. Increased acidity reduces the ability of mollusks and crustaceans to make shells and corals to make their homes. In this diagram, you can see how carbon dioxide enters the ocean, resulting in carbonic acid, an increase in the level of acidity, a lower pH value, as carbonic acid dissociates into hydrogen ions and carbonate ions. The color change in the diagram, left to right, indicates an increase in acidity. Notice how the diagram indicates deformed shells of animals. Ocean acidification causes a loss of biodiversity. Mollusks and corals, both of which need to build calcium carbonate shells or housing respectively, fare poorly under ocean acidification. You can see in this graph that the amount of calcification decreases as the pH decreases. As oceans become more acidic, corals suffer. Acidic conditions results in the dissolution of calcium carbonate. The calcium carbonate housing of corals dissolves in the acidic conditions. Added carbon dioxide to the oceans causes ocean acidification. Acidification dissolves calcium carbonate. Corals are likely to suffer, a condition known as bleaching, as we can see in this image. A loss of shellfish, animals that make calcium carbonate shells, would reduce the income, if not the entire livelihood, of people who harvest shellfish or serve shellfish in restaurants. Oysters, clams, and scallops is a $400 million per year business in the United States. Corals are habitats for many species, sponges, crabs, starfish, and many species of fish.
25% of all marine life is dependent on coral reefs. The loss of reefs would reduce tourism from snorkeling and dive tours. There is economic impact and a degradation of the environment for those of us who appreciate biodiversity.
The effects of climate change on ecosystems are an increased rate of melting of the Arctic ice cap, loss of the ice habitat, potential loss of the polar bear, a thaw of permafrost in summers, methane release due to increased rates of decomposition of detritus, shifts in weather patterns, more energetic weather, a northward shift in biomes. The thermal expansion of water would raise ocean levels, a greater success of pest species including pathogens. The melting of the Greenland ice cap would raise world ocean levels, loss of coral due to acidic oceans, and warmer oceans. And that brings us to the end of IB Bio Ecology Core Part 4.